In this research paper titled, Magic: Near Optimal Data Attribution for Deep Learning, authors Andrew Ilias and Logan Engstrom from Stanford and MIT explore a key challenge in machine learning: understanding how changes to training data affect a model's predictions. Let's break this down step by step. First, imagine you're training a deep learning model, like one that recognizes images or generates text. The model learns from a dataset, but what if you want to know exactly how adding or removing certain data points would change its behavior? This is the core of predictive data attribution. It's about estimating the impact of modifying the training data on the final model's outputs. In simpler, convex machine learning settings, where the loss function is straightforward and has a single minimum, tools like the infinitesimal jackknife make this easy. These methods allow you to calculate, with high accuracy, how tweaks to the data would shift the model's predictions without retraining everything from scratch. However, in the real world of large-scale deep learning, things get complicated. Models for tasks like computer vision or natural language processing often deal with non-convex loss landscapes, meaning there are multiple local minima and the training process is highly unpredictable. Existing methods for data attribution in these scenarios fall short. Their estimates typically only show weak correlations with the actual ground truth effects, and they often have large errors. For instance, when you try to predict how removing a subset of data would change predictions, the results might not match reality very well. The paper highlights this gap by pointing to previous work, such as studies on influence functions and other attribution techniques, which work fine in controlled environments but struggle with the randomness and complexity of modern neural networks. This randomness means that even training the same model twice on the same data can lead to different outcomes, making it hard to attribute specific predictions to particular data points. Now, the authors introduce their main contribution: a new method called Magic, which stands for a technique they describe as combining classical statistical approaches with recent advances in metadifferentiation. Metadifferentiation is a way to differentiate through the entire training process, essentially treating the optimization algorithm itself as something you can analyze and adjust. By blending these ideas, Magic aims to provide near-optimal estimates of how adding or removing training data would affect model predictions. Specifically, Magic focuses on counterfactual scenarios, like what would happen if you deleted certain data points from the training set. The method is designed to be more accurate and efficient, especially in non-convex settings. The paper claims that Magic achieves estimates that are highly correlated with the true effects, much better than state-of-the-art baselines. To illustrate this, let's look at the results from Figure 1 in the paper. Here, they compare Magic to two other methods, EK-FAC and TRAC. For a series of experiments on the CIFAR-10 dataset, which is a common benchmark for image classification, they randomly removed 1% of the training samples and measured the impact on the model's loss for test points. The left side of the figure shows Spearman correlation coefficients, which measure how well the predicted losses match the actual losses. Magic achieves an average correlation of around 0.96, which is nearly perfect, while the baselines only reach about 0.23 to 0.35 even after rescaling. On the right side, they plot predicted loss against true loss for different subsets of data. Magic's predictions align closely with the true values, forming a straight line, whereas the baselines are scattered and require rescaling to even approximate the correct scale. This demonstrates that Magic not only correlates well but also gets the absolute scale right, which is crucial for practical applications. For example, if you're trying to identify which data points are most influential in causing errors, you need both accurate rankings and precise magnitude estimates. Beyond the method itself, the paper introduces a fresh perspective called single model data attribution. Traditionally, data attribution methods predict how a new model, trained from scratch on a modified dataset, would perform on average. But that doesn't account for the specific model you already have, which might have its own unique behaviors due to random initialization or training quirks. In the single model approach, the goal is to estimate how your particular existing model would have turned out if the training data were different. This is a subtle but important shift. It means we're not averaging over possible trainings. Instead, we're trying to simulate changes directly on the current model. This could be useful in scenarios where retraining isn't feasible, like in production systems, and it addresses the inherent variability in deep learning. The authors argue that this perspective makes attribution more reliable because it ties back to the actual model in use. They build magic around this idea, using techniques that leverage the model's parameters and the training dynamics to make these predictions. Overall, this work advances the field by providing a more effective tool for understanding data's role in model performance. It has implications for areas like data efficiency, where you might want to prioritize high-impact data, model debugging, to remove problematic examples, or even ethical AI, to assess biases introduced by specific data sources. In their experiments, Magic shows strong performance across various setups, suggesting it's a versatile solution for deep learning challenges. By combining established statistical tools with modern optimization insights, the authors paved the way for more precise and actionable data attribution in complex, real-world applications.